Welcome to sprite tutorial number 4 for the ZX Spectrum Next in NextBASIC. Okay, we're still on the pac-man game and we're still on the subject of collision detection. So I'll just take the listing down here to where we handled collision. Here it is in lines 3010 to 3030. So this line here, 3020, this is where I handle collision and it does 4 checks. So we covered that last time. I'm not going to do it again here, but there's a better way to do this. And it was suggested first by Scott Ager and again by Yue Geiken. Sorry if I pronounced your name wrong. So I'm going to just ram that out so it doesn't function. And we're going to do a different line. It's kind of similar, but it's much more efficient. Before I do, hold on, I'm getting ahead of myself. I want to run this. First of all, let's make sure we're in the highest megahertz. I want you to get a sense of the speed of the game, or lack thereof. Right, that's how. So try to remember how fast that's going or how slow that's going, depending on how you look at it. Because when I make this change, there should be a difference. Right, so let's put a remark in front of that line so it doesn't run. Ultimately we're going to get rid of it, but for now, just so we can compare the two things, we'll leave it on the screen. So what I want to do is use a function called abs, ABS. Now here's what this does. If you do ABS in front of something, for instance, the expression ABS minus 4, well, that equates to 4. The expression ABS 3 equates to 3. The expression ABS minus 6 equates to 6. Basically, it just turns negative numbers into positive numbers and it leaves positive numbers as positive numbers. So here's how we're going to use that. I'm going to use, just to make this clearer, I'm going to use some variable names that don't actually exist in the program, just to explain how this works, and then we'll replace those variable names with the real ones. So let's say I mean GI, these are confusing variable names, so I want to use one that makes better sense. If we say the enemy's X position on the screen, the enemy's horizontal position, if we call that enemy X, and if we take away the player's X position, we'll call the player X. So the enemy X minus the player X, and we do an abs on that. Now here's where we have to be careful, because if I leave that like that, that expression won't work properly. It'll treat it as if it sees this. It'll calculate ABS enemy X before it takes away player X. I don't want that. I want ABS followed by brackets. I want the ABS of this expression, enemy X minus player X. Now here's what's interesting is, we really want to get to whether enemy X and player X have a relationship of 16 pixels or less, meaning they're within 16 pixels of each other, colliding in other words. So depending on whether enemy X is to the left or the right of player X, that will determine whether the enemy is on, well, it'll determine whether you end up with a negative or a positive result. So we just want to end up with a positive result, which is why we're applying abs to it. So if in the gameplay this resulted in negative 15, well, we're going to turn it into positive 15 by applying ABS. And to detect collision, we want to do is less than 16. So that combines this and this, these two expressions, into one expression. Now to do the Y, it's exactly the same logic, and enemy Y minus player Y, forgot my abs, is less than 16. Then go to your player death routine, which in my case is at line 9010. Okay, so this is the logic. As I said, these variables aren't the real variables, but it makes it clearer what's happening if I can put something closer to how you understand these in plain English. If the enemy's horizontal position minus the player's horizontal position with abs applied to it is less than 16, and the enemy's y position, vertical, and the player's vertical position subtracted with abs applied is less than 16, then go to 9010, right? So let's now replace these with the actual variable names that we're using in our game. So the enemy's x is called g brackets I, because we're using an array because there are 4 enemies. So you have to cast your mind back to the last tutorial to get a sense of what that is. The player is just called x, it's not called player x, there's it there. That's the enemy, that's the player, okay? So the enemy's y position, I used an h array for that with I after it, minus the player's y position, and I just used y for that. There we go. That's our line complete. So I'm leaving the for next loop intact because I want to go through all the i's, 1, 2, 3, and 4 for the 4 ghosts. So we've turned off, as you can see, our original line that detects collision. We've now introduced a new line, different one. So I'm going to now fully get rid of that first line, 3020, we don't need it. So this is the only line in the entire program that's handling, well, in conjunction with for and next, that's handling the collision of the 4 ghosts with the player. Shall we see if it works? Now, is it running any faster? I could swear it is. I'm not entirely sure, but I think it is. And it would make sense that it is because we are now using 2 expressions instead of 4. So let's see if the collision works. And it does. Very nice. Okay, so that's one way of doing collision. And I would strongly advise you to put this in your notes and keep it handy because I reckon I'm going to be using this many times in the future as I program arcade games. But cue drum roll. There's an even better way of doing collision, right? So I'm going to erase not just line 3025. Let me just erase that, 3025. I'm also going to erase that entire for next loop. And I'm going to handle collision with only one line. Now I'm going to write it out first and then I'm going to explain it, and it's going to look absolutely terrible to most of you because it's closer to the sort of thing you would do in machine code than in BASIC, but I'm delighted that we can actually do this in BASIC. So here goes. I'm going to write it out and test it, and then I'm going to explain it. There we go. Okay, you understood that, but at least go to 9010, which is go to the death routine. So basically this if and this means if collision happened. So do you believe me when I say this is going to actually work for all the collision? Watch this. Now look at how fast it's going. Yeah, that's even faster than before because we've reduced the logic really significantly. Let's check if it works. Look at that. Check with... Now, it happened a second time. We'll get to why that happened a second time in a moment. Let's try one of the other ghosts. Yep, it's working. So, why is it working? I'm going to do my best to explain this. Right. I'll take a rem line here just for the purpose of being able to type and letting you see what I'm going to type. First of all, we use the keyword in order to read a hardware port. Now, a hardware port is any point of communication between the inside of the spectrum and the outside world. Well, loosely speaking, that's what it is. The keyboard works across several hardware ports. Your joystick has a particular hardware port. Your edge connector along the back is a hardware port. But also, hardware ports exist between the spectrum and the hardware sprites. So this is a point of communication between the spectrum and its hardware sprites. So port 12347 specifically handles some things about sprites. So at any moment, that port is going to have an 8-bit value in it. Okay? So it could be 240, it could be 25, it could be 32. But the key thing I want you to remember here is that that number doesn't mean a whole lot in decimal. However, it means a great deal in binary. So as you know, I can represent any 8-bit value in binary like this. So that's the binary value 1. Okay? So let's say, just for the sake of argument, that at a given moment, port 12347 happened to have in it the binary number. Is that 8 values? No, it happened to have that value in it, right? Oh, what have I done? Why did I do 9020? This is where you make a mess of your program by typing the wrong number and erasing part of it. Okay. I think I can remember what should be in there. Bear with me. Yeah. That's better. Silly me. Now, where were we? Yes. 302. That's where I needed to be. Okay, so I can't remember what binary number I did there, so I'll just pick another one arbitrarily here. There's a binary number for you. And let's imagine that that's in that port. So one of the things I'm used to in machine code, and I've done a little bit of machine code dabbling, not a huge amount, I'm certainly not an expert in it, but I do understand how AND, OR, and XOR are used in machine code. So you can see there's a little AND symbol here. Now, you're familiar with how AND is used in BASIC. You know expressions like this. If x is, let's say, greater than 0 and x is less than 10, then... So you've seen expressions like that. You know what AND does. It means that then, the consequences of then will only be executed if x is in the range 1, 2, 3, 4, 5, 6, 7, 8, or 9. And means this must be true and this must be true for this to be executed. Okay? You also know how OR works. It's, if x equals 0 or x equals 10, this will be executed if x equals 0 or x equals 10. If I had an AND in it, in that case it wouldn't make any sense because x can't be 0 and 10 at the same time. Okay? We don't have XOR, exclusive OR, in BASIC. But we do now actually. That's been included. I'll explain something about exclusive OR later. Maybe it's not entirely relevant to our current example, but it is now part of BASIC. Not in that fashion, but anyway, we'll get to that. So, that's AND spelt explicitly A-N-D. But what's this AND that looks like that? Because we're using this instead. This is called the Bitwise AND operator. And what it does is, it compares two binary numbers. And it's specifically binary. That's what we mean by bitwise. It looks at the bits of a number, not its decimal value. So for instance, if we say that this number is currently in that port 12347 and we apply the bitwise AND operator to it with this value, binary 1, 1, 2, 3, 4, 5, 6, 7, 8. What is the outcome of saying that and that? Well, I'll take a new line because it's easier to see it on a new line. 3030. Ram. Whoops. Ram. Okay. And on the next line then, we'll do the result of that. Equals. Right. It helps to space it out like this. Okay. Let's see. So that's it represented as you would do addition when you were in primary school. You know, 2 lines and then an answer on the bottom line. So what we're doing is this and this means this, bitwise and this. So here's how it works. If this bit and this bit is a 1, the answer is 1, otherwise it's a 0. If this bit and this bit is a 1, it's a 1, otherwise it's 0. Both bits must be 1 for the result to be 1. So it's 0, 0, 0, 0, 0, 0. So that's what would result from that calculation being done. So I'm asking if that expression, this with this, equals that expression. So does that equal that? No, it doesn't. Then you won't go to 9020. That's how that would work out. Let me give you a different binary value, right? Let's totally change this. Like so, right? So there's another binary value that might just happen at any given moment to be in that hardware port. We AND it with that, and here's the result this time. Still 0, still 0, still 0, still 0, still 0, still 0, still 0. But look, there's a 1 and a 1 in this bit. So the answer to that one is 1. And this now means if 00000001 equals 00000001, and does it? Yes, it does. Then go to 9020. So if this number happened to be in that hardware port, we'd go to we'd go to the death routine. So what we're actually doing here is we're examining this bit here, bit 0, very carefully. And it works like this. Bit 0 of port 12347 handles hardware sprite collision. And it handles it automatically. You don't have to do anything. If a sprite is colliding with another sprite on the screen, there will be a 1 in the rightmost binary digit, bit 0. If there's no collision happening on the screen, there will be a 0. And that's how it works. And it's very, very useful. So, unfortunately, I can't do this line. Here's the problem. Here's why I need this bitwise AND operator. If I had structured, I'm just going to retype 3010 as 3010. If I had structured it like this, if in 12347 equals then go to 9020. Why can't we just do straightforward logic like that, okay? If this port reads a 1 in the rightmost binary digit, then go to 9020. The problem with that logic is that the entire number has to be binary 1, okay? But these other things within port 12347, these other binary digits are doing their own thing. And we need the collision detection to be active regardless of whether these bits are 1 or 0. We only want to pay attention. We want to isolate binary bit 0, bit number 0, okay, at the right hand side. We want to detect what's going on in there while ignoring everything else. And that's how we do it. The bitwise AND operator. Okay? I hope that makes a little bit more sense. We're going to go into this a little bit more in the next lesson because I've got Kempston joystick support working, and I've got a different way of reading the keyboard that allows for diagonals. And we're going to be using this sort of thing again. And if anything, this is actually a more complex example than the one I'm going to show you next time. The bottom line is, if you don't understand this, you can still use it, okay? Now you may be wondering, where does it decide which sprites are colliding? It actually is applied to all sprites. So if any of the 64 hardware sprites accessible to BASIC, if any of them collide, this bit 1 will be active. And if any of them are not colliding, bit 1 will be inactive. Every time it detects a collision, it sets the bit back to 0 again afterwards. So a little bit of a shout out to Roberto Maloney. He's the one that first pointed out port 12347 to me and how it behaved. And as soon as he did, I realized I was going to be able to use it from BASIC because I'd already played with this bitwise AND operator. I think it's covered in chapter 7 of the manual. Gary Lancaster also weighed in. He's the one who developed NextBASIC. He also weighed in and pointed out that I can actually shorten the expression considerably. Binary 1 and decimal 1 are the same number. Binary 2 and decimal 2 aren't. Binary 2 is 1, 0. But the only two numbers that are the same in decimal and binary are 0 and 1. If you go any higher, they're not the same. So you can actually shorten this expression to just 1. Okay? And you can do the same here because, again, it's just binary 1. So that makes it a lot smaller. But part of me likes being more explicit with it, although I don't know if that has an impact on the running of it. If you're wondering why we have a percentage symbol here, it's because this only works with integers. You have to basically force it to treat it as an integer expression. So you put the percentage symbol before it and that applies to everything after. So integer value in port 12347, bitwise AND with binary 1, does it equal 1? So that's fine also. And then Gary pointed out that I can shorten it even further. This equals 1 is redundant. Again, I like having it there because it makes more sense when I'm looking at the program. But as far as I know, the reason why it's redundant is because 0 equates to false and 1 equates to true. And the result of any if instruction is always true or false. So if the answer ends up being 1, you don't have to explicitly say a 1. So you can just do if in 1, 2, 3, 4, 7 and 1, then go to. There you go. So that's a big long expression, considerably shortened to that. But when you shorten it to that, it's harder to understand what's going on, unless that's why I showed it to you the long way around. So let's remove 3015. And let's remove my, well, I'll not remove those yet because I'll maybe explain OR logic and XOR logic to you just while we've got that on the screen. First of all, let me run this, make sure it's working. Now, this is interesting. I died instantly even though I'm not touching anything. The reason why that happened was because the last time I ran the game, I died and then the collision bit was active. It was a 1. It was set rather, that's the right terminology. When a binary bit has a 0 in it, we say it's reset. And when it has a 1 in it, we say it's set. So the binary bit 0 of 1, 2, 3, 4, 7 had a 1 in it at the end of the game. So it had a 1 in it at the start of this also. And that's why it immediately killed me. So it actually makes sense to do a line like that, 3010, somewhere near the start of your program, like say where I'm defining my variables. So I would say I'm going to add line 170. Okay, and I don't want to kill the player, obviously. This is just getting it to read the collision bit and then if there's no collision, it'll automatically turn to 0. So I basically just want to continue. So go to the next line, which would be 180 if there was 180. So check the collision bit and then just move forward. That's all I want to do. So let's see, if I run, yeah, it's working. I'll get myself killed here. There we go. I've done something to the death routine, haven't I? That time I messed up the line. But we're just testing collision, so don't worry too much about it. Now let's see, it shouldn't kill me this time. And it doesn't. Until I actually want to get killed. There we go. Now the beautiful thing about this collision bit is that it's not treating your sprites like a box. It's actually getting into the defined shape of the sprite. So if you did a round sprite, it'll only collide when the round edges of your sprite actually touch another one. I'll test that to show you. I'm going to touch Pac-Man in the corners the way I did before. See that? We couldn't get that sort of accuracy before, but we can now. Obviously, it's a drawback when the collision bit becomes set when any sprites collide. So in your game, if your ghosts navigated around paths that ended up with them going on top of each other, it would set the collision bit. So you'd have to be a little creative in how you code this so that that would avoid that happening. Or you could do a combination of checking the collision bit. You could check the collision bit in the hardware fashion by reading that port, plus using the square collision routine that we already used before. So there's ways of doing it. There's always ways around it. You just have to be a little inventive. I'm just delighted that this is actually accessible from BASIC. So I strongly recommend, along with the other one, that you write down this in your notes and remember that anywhere you put that in your program, it will detect whether collision is happening with hardware sprites anywhere on the screen. Even if you don't understand it, you can use it. But if you had a hard time understanding this one, I think you'll have an easier time after the next lesson when we cover Kempston joystick support and diagonal keyboard reading. So I'm just going to briefly conclude by explaining OR. Now, you don't write OR like you would when you're doing a normal OR expression. You do a vertical bar. Now, where is that on the keyboard? Because I don't use it very often. There it is. Vertical bar. So, OR logic applied to this would go like this. I'll delete this. And I'm pretty sure you know this already, most of you. So, if this bit or this bit is a 1, the result is a 1. If this bit or this bit are 1, the result is a 1. It's not. Same with that one. If this bit or this bit is a 1, it's a 1. If this bit or this bit is 1, 0, and 1, 0, both are 1, so that would be a 1. Okay? That's how that works. Now, exclusive OR is a little different. XOR as it's represented in English. You activate bitwise XOR by doing an upward pointing arrow, like so. And here's how it differs from OR. It has to be exclusive. So that's a normal OR. One of the bits is active, is set, one of the bits is reset. Only one, exclusively one. So that's a 1. Nothing there, so that's 0. Nothing there, 0. Only one is active there, 0. Whoops. 1, 0. Now, here's how this one's different from OR. It's only set when one of the bits is exclusively 1 and one is still 0. So that actually results in 0 because it doesn't meet the criteria of exclusively OR. Right? That's exclusively OR. Only one of the bits is allowed to be 1. When both are 1, it's 0. And you might be wondering, well, why is that? What would that possibly be useful for? Well, one use is, let's say you wanted to flip all the bits. you could use that kind of logic. You could do any number exclusive OR with 255, that's the binary equivalent of 255, the maximum value of any 8-bit number. Watch what happens when you exclusive OR this. Both of those are 1, so that's not exclusive, it becomes a 0. Only one of those is a 1, that is exclusive, it's a 1. Same with that one. Not exclusive, 0, exclusive, 1. Not exclusive, 0, exclusive, 1. Not exclusive, 0. Look what's happened. If I take this line away, if I take the middle line away, you'll see what's happened. 3030. Look, all the bits have been flipped to their opposite value. So that's one of the things that exclusive OR is good for. I encountered this, as I said, in machine code, in assembly language programming. But I can see that there may be a use for it at some point in BASIC, and I'm very glad that it is accessible in BASIC. So I went a little bit beyond the bounds of what we needed to do, but I thought I would cover that. Anyway, that's probably the end of everything we're going to do regarding collision. I asked Gary if there's anything more built into the hardware that is accessible via machine code that we haven't got here in BASIC, and there isn't. That collision bit is the only way to check collision in machine code, and if you needed to do it in a more elaborate way, you have to write machine code routines that do that square box type collision that we were already doing, which would of course be faster than it is in BASIC. Or you'd have to do your own sprite routines that create sprite masks. That's just how we would have done it back in the 48K days. So we have very good tools here in BASIC for handling sprites. It's just the fact that this is a BASIC interpreter rather than a compiler makes it quite difficult in terms of maintaining a good speed. So the one thing that I would like to see happen in NextBASIC more than anything is a compiler that'll basically handle anything you can throw at it, and we should see pretty dramatic speed increases going on in games. But of course there are ways to be inventive to pull greater speed out of a game. One of the ways, just before we finish up, is to actually not move things 1 pixel at a time. So first of all, have a sense of what the speed is just before I make any changes. There's your current speed. So look at how fast the ghosts are moving. If I really wanted them to be faster, there's the line that handles ghost movement. Instead of moving them 1 line at a time, just move them, 1 pixel at a time, just move them 2. Okay. Right, I made a mistake. That is handling the ghost pattern. Leave that alone, leave that at 1. This is the part that handles the ghost movement. Right, this is what I need to put to 2. The ghost should now move twice as fast. I'm a little bit concerned about 303 in there because that's an odd number. That's when the ghost reaches the edge of the screen here and flips back to the left hand side. So I'm going to try 304. I need an even number, otherwise it'll skip because we're moving forward. What if the ghost start position is an odd number? Okay, tell you what we'll do. I'll do greater than 303. Yeah. So if the ghost exceeds any horizontal position greater than 303, moving back to the left hand side. Now I haven't changed the player speed, so let's see how fast the ghosts move now. Look at that. Now that still looks pretty good in terms of animation, but we've just suddenly dramatically increased the speed of the game. And collision should still be fine. Yep. Let's change the player speed too then. So player movement is handled via the subroutines. Instead of let x equal x minus 1 for moving up, let x equal x minus 2. Moving down is yeah, and you're going to see I've got some stuff in here for handling attribute collision. It's not perfected yet, so pay no mind to that. Okay, we'll just stick with up just to test how fast it looks. So here's down, but here's up much quicker. So you can see now how we can still make a very nice fast moving Pac-Man game just by changing how many pixels you move at a time. Alright folks, hope to see you all next time for the next tutorial where we're going to cover joystick control and diagonal movement.